Hello, everyone, and welcome to Rational Science, directly from Frankfurt, Germany. And today we have a nice show. We're going to be doing, like we always try to do lately, is we do extinction first, then we do a little bit of physics, and then we're going to get into the questions and comments that people made since last time. And so let's start with extinction and extinction topics. There are many subjects related to extinction. A lot of people like to go along the lines of politics. Everybody's an expert in politics because it depends on whether it's your opinion, your recommendation, what you think, how you think the world should be run, that sort of thing. We're not so interested in that here, at least. We try to concentrate more on the mechanism of extinction, how it's going to happen. Okay. Okay, so let's start with extinction. And here we have a lady. I'll start with a little article that came out, and and she says Tracy Stone Manning, President Joe Biden's nominee to lead the Bureau of Land Management, argued that Americans need to have fewer children, and called American kids environmental hazards. My God, does she really believe this? We must consume less, and more importantly, we must breed fewer consuming humans. And one lady that they quote in that article is not her, but someone else said, "It would be my third baby, but there's not a population problem here like in Africa or India. And besides, smart people like Bob and me should be the people having kids." Okay, should we have fewer kids? Maybe they should do the what is it, like the Chinese did? You know, the one child per family rule. You can't have more than one kid. Is that what we should do? Maybe, you know, just put a law there that if you have two kids, we got to kill the second one, or put you in jail, or fine you, or whatever. Okay, another issue related to extinction, a little more related to extinction, I guess. This is Michio Kaku, and he's a futurologist now. He tries to tell us what the future looks like. See, all these people are into predictions. Once you study math, mathematical physics, then you become an astrologer. That's the next step. You make a lot of money just making predictions. And he quotes Carl Sagan, Jeff Bezos, and Elon Musk. And he says for Carl Sagan, that one day Carl Sagan told him this. He says, "An asteroid will hit us one day. We have to make humans a two-planet species." What was Sagan talking about? Well, he was talking about, if we happen to screw up this planet, maybe World War III, or we pollute it, or whatever thing, well, then we have this other planet where consciousness can continue living, intelligence. And sometimes I wonder how much intelligence these people really have. Jeff Bezos, he says, we have to make the earth a grand park. Okay? We should relocate all polluting industries to space or to the moon. And this should be just a garden. Okay? Is that ever going to materialize? Is that ever going to happen? We're going to move all the heavy industry, all the polluting industry. Yeah, no problem. You want to pollute, go to the moon. We'll pollute the whole moon. After all, it's just a stone out there. We just got to transfer all the production over there. And here we live, I guess, doing services all day long, robots serving us. Great life, huh? I think these people think a little too much, or maybe they're not enough, I guess. Then Elon Musk, he's the SpaceX project manager, I guess you could say. He wants to create a multi-planet species. We should go to several planets. He wants to ship 1 million passengers to Mars. 1 million people. Like several trips, little by little, when we populate at least a region of Mars, we'll have 1 million people there, hopefully self-sustaining, which is what he's thinking about, okay? And here's a little more detail of what Elon Musk is proposing. Give me a second here. This is what he's proposing. He's saying multi-planet species and safe spacefaring civilization. We're going to be floating in space, going all around. Our future is in space, the final frontier, Ensure continuance of consciousness. Okay, that way we guarantee that consciousness will not die. Okay, is it a problem if it does? Don't you think that even if consciousness dies here on Earth, there's going to be some other planet out there in the middle of nowhere that also creates consciousness, just like the Earth did here? Maybe there is a planet somewhere out there already, far away probably. Okay, so the fact that consciousness dies here on Earth and that we didn't get to go to the moon or to Mars or anywhere, and then someone turns the light out on the Earth, is that a problem? I mean, I think you should worry about yourself, okay, and not have these idealistic things for all of humanity. Okay? People take decisions for all of humanity here. He wants to put a self-sustaining city on Mars. If ships from Earth stop coming, for example, World War III, right? That's what these people are thinking. Can the city sustain itself? Okay, and it must happen before World War III, because if we do it if World War III happens first, is there any chance whatsoever that we can create a colony on Mars? So he's suggesting that we should have this rush to hurry it up before that World War III comes around, okay? I guess people are fearing that will happen. I guess if you ask a lot of people out there, do a poll or whatever, I'm sure a lot of people will say that they think it's very possible. Now, what percentage, I don't know. They have that doomsday clock there, and they keep moving it back and forth, depending on, what's going on in the world. Sometimes they move it closer to 12 o'clock, sometimes closer to 10 o'clock. It goes back and forth, that hand on the clock. How close are we to 12 o'clock, meaning Third World War III? And will that be the demise of man if we go, if we have a war of that nature where we throw the nukes, the bioweapons, we talked about that a little bit the other day. If we throw the nukes, if someone presses that red button, will that be the end of man? Okay, or will someone survive and restart the world again? Okay, keep that question in mind. Okay, we'll see if we can address that. Okay, fellow says, and again, here we have the political aspect of extinction. Bill doesn't know and doesn't believe about the existence of great powers like the financial credit elite and Zionism and Christian Catholic, Apostolic, and Islam and blah, blah, blah. He doesn't know and doesn't believe that the world politics are under these great powers. And he knows and he believes that the state and the state governments are in charge. Well, the first thing we have to do is put it in the right context. Belief is not a part of science, okay? Belief is part of religion. So irrespective of what I believe, it's got nothing to do with science, especially in this case with extinction, which is the mechanism of extinction, okay? So whether I believe in this or that doesn't matter. The first thing we have to point out is this. Put it on the other side. Give me a second. What happened to it? Oh, I see what happened. Give me a second here. Put it behind the other one. Okay. This is the scientific method. Okay. What is science? Rational explanations. And where in the scientific method, which goes under that, step 1, step 2, step 3, where do you find belief? Okay? In the scientific method, we make assumptions, and then we build the theory on those assumptions. So you can make an assumption that Zionism is out there and that Catholic Church is doing something, that Islam is doing whatever, and you can make any assumption. And then build your theory upon that so that we can understand what's going through your mind. We can understand your theory. But just to say that, Bill doesn't believe, well, you haven't said anything. We don't know what you're talking about. What is the conclusion? What is your theory? That's what we wish to know or understand. And so, without that, you have nothing, at least for this channel. You really have to try to concentrate on science and not just say, well, he believes in this and he believes in that. We all have beliefs, and beliefs play no role whatsoever in science. So get the word belief out of your mouth. Never use it again, not here, okay? Unless you're saying, well, the religious folk believe. That's fine. You can say something like that, but not in the context of science, okay? Don't bring the word belief. Okay, another issue someone raised. Fellow says, both people in a trade are buyers and sellers. Because I talked about the fact that, well, I'll get into that in a second, but essentially, I put the other day that you have three situations. You have the buyer, seller, and seller, seller. Okay, and that's what he's addressing. And I'm saying that seller, seller is the only one that's capitalism. Buyer, seller is communism. And buyer is leisure, unemployment, manna from heaven. Okay, so that's the context in which I put these two words, buyer and seller. And he's addressing that. He says both people in a trade are buyers and sellers. Well, he's just repeating the party line of what everybody out there thinks, or the way they look at these two words. Okay, he hasn't put anything new. In fact, I don't think he understood what I said at all. Okay, if you had a boat and I have money and we trade them, then I bought a boat by selling you money and you bought money by selling me a boat. Yeah, in other words, he said the same thing that everybody else says. So he didn't understand squat. Okay, but I'm going to the next part there. Transaction is capitalist as long as it is voluntary, meaning no force or coercion was used. You needing food to survive doesn't count as involuntary because that is forced onto you by nature, not humans. Okay, so yeah, again, I don't think this fellow understood anything of what I said. So let me repeat it. Okay, here it is. Okay, that's the situation. You have these three different situations. One is where you have a buyer and a seller. Okay, buyer and the seller, that's known as communism. It's not known as capitalism, it's known as communism. Why? Because we have to look at what the buyer is doing here, okay? If you just look at the buyer, you don't know if he's giving something in exchange. And I'll get to that in a second, okay? But here are the three categories, essentially, or three situations. Then you have the buyer, the guy who receives manna from heaven. He's served by robots. Nobody works on planet Earth. There's not even a government. There's no military. You're just receiving stuff free from who knows what. Maybe the robots are working the land. If Jeff Bezos has his way, they're working in Mars or on the moon. And they're bringing the stuff to you from over there, grapes and whatever they are planting and harvesting up there. And they bring them over here, all done by robots. And all we do, all 8 billion, 9 billion, 10 billion of us, however many we are at the time that this happens, we all receive. And we all receive all this free stuff from heaven. So we're all buyers. We're not giving anything in exchange. Okay? And then, of course, you have the capitalist, which is the true capitalist, which is the seller. There are no buyers in capitalism. There are only sellers, okay? And you say, Bill, what the hell are you talking about? Okay, so let's find out what I'm talking about. Let's define these terms so that we can use them consistently. I'll show you what I'm referring to, okay? A little more detail than the other day. Seller, what is a seller? This is out of the dictionary. No special word here, okay? But I'm going to cut it short. I'm going to cut it where I should cut it, or where I think it should be cut, okay? A person who sells, okay? Gives. No inkling of anything else, whether he's receiving anything in return. It just sells. I'm giving something away, okay? For now. Just bear with me, okay? Now, we look at sell. It says to transfer goods or render services. And then they have that little piece saying, saying in exchange for money. Or you could put anything in there, in exchange for something, okay? And so that's where we have a problem. Seller, should we stop at the just gives away and not talk about what he receives in exchange? Seller just gives. Okay, that's my proposal. I'm saying he's just a giver. Okay, what is a buyer under this proposal? Well, a buyer is a person who buys. So we look up the word, which means receives. We look up the word buy. Okay, it says to acquire the possession of or the right to, and then they add, by paying or promising to pay an equivalent, especially in money, purchase, blah blah blah. And I'm saying we should take that last part out, what's enclosed in green there. I think we should say buyer is someone who receives. So one is a giver, the other one is a receiver. Now, you have situations like, someone gives and doesn't receive. We call it donation or donator or donor. Okay. And if he takes without giving, we call it stealing. Okay. So we have all these nuances in between humans, because this is all human stuff. The rest of the animal kingdom typically doesn't do trade. They do stealing. I've seen hyenas take away from cheetahs and from other lesser animals, weaker animals, and they just go in there and take whatever they think they can get. So they do steal. There is stealing out there, okay, in the wild kingdom. But in general, these are the situations. What am I talking about? Well, this is what I'm talking about. Let's go into a little more detail. Okay, here it is. We have to distinguish between a buyer who receives without giving, okay, and a buyer who receives and does give. We call this one capitalism. If he gives something in exchange, right, it's capitalism. And if he gave something, he's a seller. Okay, he gave something, he's a seller. Okay, and if he receives something without giving anything in exchange, well, we call that communism. The government or whatever, welfare, socialism. You just receive. You don't have to give anything in return. Lenin had that idea from, or I think it was Marx, from each according to his capabilities, to each according to his needs, right? Well, what if you only have one way of flow of that, to each according to his needs? And you don't provide any of your abilities, either because there's no work, or maybe you're quadriplegic, maybe you cannot provide anything, maybe you're a veggie, and we want to keep you alive. I don't know why, but we do. And because we keep you alive, we just give you. We give you care, we give you food, we give you everything, and you can't do anything about it because you cannot contribute to the global economy in any way. So you're receiving, okay? You're only receiving. And we got to factor that guy. And in the case of seller on the bottom, we have a similar situation. We have to distinguish between the giver who receives, right? And there's an exchange there. We call that capitalism. But the giver who doesn't receive, well, we typically refer to that as communism, right? Socialism, welfare state, whatever you want to call it. And we've got all these names for it, right? And so what I'm saying here, why is this relevant in the context of the extinction theory? Well, it's relevant because I say that we're becoming more and more, okay, receivers who do not give, okay? There will be more welfare people, more unemployed people eventually. And so we got to factor the language here. We got to say, well, these people are receivers. Do they buy? Yeah, they buy, but they don't sell. Okay, that's my point. And if you buy and don't sell, you got to I call him a buyer, but the correct word is receiver. He's a receiver. And right now we don't know where he got all that stuff from. For all we know, he got it from heaven, manna, just falling down in his hands or in his lap. The only time we really have capitalism is seller-seller. Then, yeah, someone gives and the other one gives. Okay? But if it's a one-way flow, we call that communism. Okay? And so I want to distinguish the receiver from the giver. Okay? Because I'm saying more and more people will become receivers and fewer people will become givers. Okay, that's the argument. Okay, moving on here. Get another one here. One fellow says, it could be that when basically now the system breaks down, meaning extinction or approaching extinction, the global economic collapse, that's what he's referring to here, it really is built back better, okay? Meaning less communist. Okay? That last part is politics, okay? Unless he's trying to say something special, there, I don't know. But this is like saying, oh, it might be a good thing to have like a World War III, erase the board, start all over again. Okay? Will it be like that? I mean, we erase the board, can we come back? Okay, and then he says fiat currency falls to zero. Okay, says all money goes to zero. Then people begin using real money, gold and Bitcoin. So he thinks gold is real money, Bitcoin is real money, but he says all the other stuff, especially dollars and so on, that's not money. Okay, but I like his last statement there. He said, just because a currency and or government fails doesn't mean all trade ends. I tend to disagree. Okay, yeah, the day that currency fails, including gold, including Bitcoin, okay, nobody should accept that anymore because what are you going to do with Bitcoin? What are you going to do with gold? What is gold? Gold is a rock. Is limestone any better than gold? I mean, I'll give you limestone for your banana if you want, or your apple. If you'll give me your apple, I'll give you limestone, a rock, any rock you want. You want gold? Okay, I'll give you gold if you can do something with it. What are you going to do with it? And Bitcoin's a number in a computer. Once we get the hackers in there, messing around with the global internet, even Bill Gates and Jeff Bezos and all these people will be as rich as you are overnight. They just press one button, all those accounts go wacko, go out of, So, yeah, I mean, the issue is that if government falls, if the global economy collapses, meaning money will be no more, all kinds of money will be no more. The only money of any importance will be food, and it won't be money because it will be the only thing of value. In that sense, you can say it's food, it's money, but nobody will trade it. In which sense, it's not money because money is that which you trade. It's what you use, something of value that you trade, that you exchange. If you have something of value but you don't trade it, it's known as food. It's known as food after the global collapse. That's what it's called. Okay? So no, once the global economy collapses, there won't be any money, okay? Because that's the point. The point of the theory is saying there won't be any money. We will not accept money. We will not accept any kind of money for the whatever amount of food that you have, because the only thing of value will be food. It's the only thing keeping you alive. You're not going to trade the only thing that has value, which is what nourishes you in real life, for what? For gold, for Bitcoin. And just do the thought experiment. You and your buddy, you got shipwrecked, or you're marooned on an island. It's just you two, and you ended up in this different sides of the mountain, and you've got all this food that you were able to get out of the ship in a little boat, and you came ashore, and now you got all this food. And your friend, he got the treasure chest. Okay, he's got all this gold, diamonds, jewels. And he comes over and says, Joey, here, I'll give you a whole bag of gold. He just comes in here, or an ingot of gold. 1 kilogram of gold. I mean, that's worth a lot. And I'll give it to you for that banana or for that apple. Will you trade? Well, if either you're a sucker, you got mental problems. Okay, you don't understand. No, no, when you're stuck on an island, you have no use for Bitcoin. Believe me. Okay, another fellow says, even worse. He says, self-sufficiency. He says that you're going to do, see, you have two types of people. One is the um, survivor, okay? And the other one is, and that's the guy that goes out on a mountain and with a gun and a backpack, and he's going to do hunting after everything collapses. Okay, and then you have the others that plant the garden. And they say, I'm going to do some gardening. Okay, and I'm going to grow my own potatoes and my own tomatoes and everything, and I'll be okay after the collapse. Well, the big problem here is not whether, like he says, they understand how to do it. That's not an issue. The issue is not how to do it, which is a problem. Obviously, if you're a city guy, you've never been in the farm, well, you may not know how to plant. You may not know about the season. You may think banana grows, on trees or whatever, so you may need some information. That's true, but I think it's irrelevant. Anyone who's got a garden, he'll be run over, at the last moment by all people from the city, all these city folks that don't know anything about farming, and they're just going to go out there and steal. They're just going to, it's not called stealing, they're just going to eat like the locusts. They're going to swarm all over your farm. If you've got any live animals like chickens or pigs or whatever, they're going to kill them and slaughter them. What are you going to do? Just shoot every person in town? Thousands of them, many of them with guns. And then obviously they're going to take all your veggies from your garden. And if you're alone, you haven't planted very much. How many acres can one person plant? And even if you have a tractor, okay, I mean, one person, how much can he plant? And then assuming you plant a lot, I don't know, several acres because you're really good, how do you patrol that with your 6-shooter or whatever? You need a machine gun, even that won't help you. You need a cannon, even that won't help you. You'll need a nuke to get rid of all the people. They're just going to come in and eat. And then you have this little kid, eating, a piece of your corn. You're going to grab your gun, shoot him in the head. Don't eat my corn. No, so the problem's going to be security. You have no 911 after the global collapse. Okay, so this notion that we're going to survive and we're going to restart the human race, Adam and Eve thing again, it's never going to happen. Once the whole world collapses, more or less, there are going to be pockets of people here and there that survive. I think that's almost guaranteed. But they're just going to live out their lives. They're not going to be going out there and saying, oh, let's start the whole thing all over again, especially after we've wiped out all our genetic diversity. We have no genetic diversity today. Whatever pockets survive, you're going to have this, this small group, founders effect. And from there, from that wiped out genetic diversity, you have no genetic diversity among you in that little group that maybe 3, 4, 5, 6, 7, 10 people maybe. You're going to start the human race again. You're going to have children by the hundreds, assuming women don't forget what it was all about. Okay? No, and a woman would not put herself in that situation either because, you won't have all the niceties of hospitals and doctors and nurses tending to you. You're going to have the baby out there in a cave. So I don't know how many women will want to do that, especially after we've gotten used to the city life. We have all these comforts we take for granted. I'm not sure that woman is going to go out there and say, oh, I'm going to have a baby. Maybe one might have on planet Earth, but certainly we're not going to restart the race again, the human race again. Okay, one fellow says, a little more closer to my subject, which is the dinos and how they disappeared, okay? And he says, if the food pyramid that inverts were the most critical in numerous food chains, such as plankton, okay, which is the food for the food for the food for many, might that not lead to a mass extinction? Okay. Would that not explain part of how the sea creatures went extinct when the big animals went under 65 million years ago? Okay. Might not all of that be one big food chain collapse that commenced when the smaller sea creatures died and spread up the chain, going up to reptiles, large mammals, if any, and even insects? Okay, yeah, that is the theory I'm proposing. Okay, this is what you see. This is just one food chain since he talked about the seas. Okay, and here you see it. Okay, um, this is more or less what the seas look. This is just one food chain in the seas. Okay, this is at the end of the Cretaceous. Okay, and what you see here is at the bottom of the food chain you have the phytoplankton. Okay, and what is that? Well, seaweed and other algae that rely on the sun to grow and to, to reproduce and all that stuff. And then they're preyed upon by the herbivores of the sea, the small herbivores, which are the zooplankton. Okay, the zoo or zooplankton, and what they do, they're going to eat all this stuff, and they're going to live on it. Okay, so these are herbivores, and some of them are carnivores also within that group. Okay, and they might attack one of the herbivores. But then you have the bigger animals, the higher level. You can say someone talked about the higher animals. Okay, so we'll call these higher animals. They're just higher on the food chain. They can eat someone below, and so they're going to eat some of the zooplankton, both herbivores and carnivores. And then you have the big monsters like the reptiles, like the mosasaurs, and they fed on the ammonites, who were, these filter feeders and so on. And you also have fish in between. I didn't put all the animals, that should have been in that picture. I'm just showing you a very small food chain, and that's more or less what it looked like. Okay, and so yeah, one of the issues that we've verified, okay, through the layer of rock. Okay, and you can look up some of these papers that have been written out there. There's several of these. Okay, so it's not like one paper out there that says it's several of them. It's like a consensus among the paleontologists that this is the description of what they see in the rock. What do they see? Well, they see that the big, the major, the big ones, the big plankton were the ones that went away at the KT boundary, essentially. Some went over the boundary and lasted a few more years, but essentially what died out close to the KT boundary were the big foraminifera, diatoms, and so on. These animals and phytoplankton disappeared, essentially, most of them. And that was the food that the ammonites depended upon. And the mosasaurs primarily fed on ammonites, and there were ammonites all over the place. Ammonites are used as an indicator fossil for almost the entire life on Earth. They look at that because they were so numerous in every age. Okay? They were very numerous, and they had hard shells, so that survived to a great extent, and so they're used as indicators. Okay, and yeah, so we know that the ammonites disappeared at the KT boundary, and that's what the mosasaurs ate, and they disappeared at the KT boundary. And so the question is, did they disappear because an asteroid hit the Earth, which is what the reigning theory is out there? Well, that asteroid would not be able to explain selectivity. And here you can explain selectivity, for that whole food chain that you see there, simply by noting that the plankton that they ate also disappeared at the KT boundary. Okay, so that's the point there. Okay. Okay, next issue is that, like I always like to say, you have to do, and if possible, it's recommended. You are urged to do this, to do Extinction 101 before you do Extinction 102. 101 is animal extinction, animals that actually died in the past. So once you figure how they died, how they disappeared, how they became extinct, maybe you can extrapolate that mechanism to man and say, well, which is Extinction 102, and say, well, can man do anything about that same mechanism? And, the person who just treats it very superficially usually says, man can do anything. We can solve any problem. We can look ahead. Our intelligence allows us to look ahead, fix any problem that comes towards us. Well, there are certain things we can't do. We can't live forever, no matter what. Otherwise, we would have invented the machine that does it, or the drug, or whatever, the food. We can't have babies anymore. You say, what? What do you mean? Yeah, we can have babies. No, we can't. We're not having babies. We're having fewer and fewer babies. So that lady at the beginning of my talk here didn't have to worry about that. They don't have to put a one child per family or two child per family law. We're not having babies. We're not having babies because we moved to the cities, and what takes over are density dependent birth rates. So we're not having babies because couples in the city don't have babies. Cities are no place for a baby. It was in the countries where our great grandmothers, and so on, had 10 babies. Half of them died and 5 continued living. No problem. Today, we're not having babies to begin with. We have one, maybe, and treat them like a god. Is the only baby you're gonna have. So, oh, he looks like me. I'm gonna. And they're expensive, and then you don't have time for them anyways. You get a babysitter to take care of them because you got to go to work, and so on and so forth. So no, we're not going to have 10 babies anymore. No woman's going to do that. And so partly because they're expensive, and the culture in the city develops in a given way, and that was inevitable that we moved from the country to the city. The other one is that there's no room in the city. Again, room also in this sense means economics. Okay, there's no economics in the city to have babies. And then what? Are you going to have an apartment that you can barely pay the rent on? And you're going to have 10 babies in your apartment? So no, the baby era is gone. We're not going to have babies anymore. One woman can have a baby. 10 women will not have a baby. That's the issue. It's a numbers issue. Okay, so no, babies are out. And yeah, just in case, here's the issue people should answer, which is what this fellow who just made the last question there, or the last comment, addressed, and that's why did the animals in the sea die at the same time as the animals on land? Okay, and if you can figure that out, okay, maybe have a clue to how the animals disappeared in the past, and whether that same mechanism, whether we humans can overcome that same mechanism. Okay. Okay, let's move on to the lecture of today on physics, and we're going to be dealing with entanglement. What the hell is entanglement? Does it mean you're tied up in knots? I'm entangled. Okay, let's look for a definition. Okay, here we have the definition from the Wikipedia, and this is what they say. Quantum entanglement is a physical phenomenon that occurs when a group of particles are generated, interact, or share spatial proximity in a way such that the quantum state of each particle of the group cannot be described independently of the state of the others, including when the particles are separated by a large distance. So if you're going to not explain, you're going to be describing, okay, very important difference in those two words. You're not going to be talking about explanation, you're going to be talking about describing. And they're saying you cannot describe certain behaviors or properties of this particle without relating them to the group. That's the first part. And the second part is it doesn't matter how far the nearest particle is to that other particle. It could be on the other side of the universe. They are what is known as entangled. They are somehow connected. One particle influences the other, even if it's on the other side of the universe. And so the only way you can describe the behavior of the particle, the target particle, is by relating it to all the other particles that are in the group. And the group is as big as you want to make it. Okay? So it could be local, it could be bigger than a house, it could be bigger than the earth. You select how far you want to take that. Okay? And again, one of the issues there that you have to keep in mind, that's where the notion of field comes in also, because you're going to give a value at each point in space. Okay, that's the definition of field, right? Says if a pair of entangled particles is generated such that their total spin is known to be zero, it's not spinning, I guess. And one, I don't know why they say zero. They say it's not spinning. I think it's easier to say that, okay? And one particle is found to have clockwise spin, right? So we're talking about spin, right? A top, right? So they said no spin, spin. We should have said, well, what is spin zero? Okay, and one particle is found to have clockwise spin on the first axis, then the spin of the other particle measured on the same axis is found to be counterclockwise. One spins clockwise, the other one spins counterclockwise. Okay, so they say that's a pair of entangled particles. Okay, so you should get the notion here that what they're referring to is that when one particle spins, just think of two tops, I guess. One top spins clockwise, the other one spins counterclockwise, like when seen from above. Okay, so you're seeing them, I guess, straight ahead from your eyes, and you're seeing them from top. And so what happens? One is clockwise, the other one is counterclockwise. And when the first top, you turn it around and turn it in the opposite direction, turn it counterclockwise, the other one instantaneously goes clockwise. And you say, well, maybe they're too close together and blah, blah, blah. No, they're saying that one could be on the moon, the other one could be on Earth, these tops. And this one influences that one. And quantum, remember, quantum deals with discrete particles. So we're talking about discrete tops here. Okay, so this top clockwise, this one counterclockwise, one's on Earth, the other one's on the moon. In fact, Brian Greene illustrates that in one of his programs, in one of his documentaries. Okay, so that's exactly what they mean. Okay, so keep this in mind. Okay, Einstein, good old Einie. Let's bring him into the show. 1935, he called it spooky action at a distance. Says, how can that be possible? That to describe one of the tops, right? I have to have some notion of the other top. Like that one's going to influence this one. And Einstein said that's ridiculous. And he didn't say it that way because he didn't want to offend the Copenhagen folks, the Copenhagen Interpretation, which was held by Niels Bohr and Werner Heisenberg and some others like Max Born. Okay, so he argued that the accepted formulation of quantum mechanics must therefore be incomplete. And I think it was his buddy Podolsky, they had the EPR, Einstein, Podolsky, and Rosen, the three guys who wrote this paper, and it's called EPR to this day, the initials of each one of their last names. And I think it was Podolsky who leaked the notion that Einstein had when he published his paper in 1935. He leaked it to the New York Times. The New York Times ran in a little article on that, and I think Einstein was not very pleased with that. Okay. So where did this notion of entanglement start? Did it start in 1935 with EPR? Einstein, Podolsky, Rosen, the paper that he wrote. I'm going to show it in a second. No, it starts here. It starts in 1927, about 8 years earlier. Okay, and it's at the Fifth Solvay Conference in Belgium. And all these gurus of mathematical physics, not physicists, but mathematical physicists, meaning mathematicians, meaning mathematicians, that's all they are. They just do equations. They met, okay, 1927, I think it was October or November. And here we have these two great men of science, Niels Bohr and Einstein, and they had a big debate. Okay, the debate was not about EPR, Einstein, Podolsky, Rosen experiment, which is this action at a distance without a mediator. Okay, no, their discussion was about the Slit Experiment. Okay, and the Slit Experiment, as some of you know, looks more or less like this. Okay, here's Einstein and Niels Bohr. I can get it up here. Give me a second. There we go. This is the Einstein experiment. He says, look, we shine a monochromatic light, okay, through two slits, and we see this pattern on the screen. Okay, we don't see just two holes; we see fringes. Okay, and so Einstein was trying to show Niels Bohr in this discussion that we could measure that accurately. And so he came up with his argument. And what happened, Niels Bohr, he was frightened because this would destroy quantum mechanics if you could measure that precisely. And so he thought about it one day. I think he came in the next day and he said, haha, I got you, Einie. And he says, look, according to your own theory, if we shine a light at the, in this case, we can call them the window sills of the partition there, of the slits. We send light at the slits, okay, and they hit the balls, the photons, right? They hit the window sills. What happens as soon as the photon hits the window sills, it's going to move the entire partition to some extent. And here I'm exaggerating, but the point is that if it moves, then you cannot know the exact position of the photons and of the waves. Okay, so with that argument, supposedly Bohr came out of that meeting, or that argument. It lasted a couple of days. Came out victorious. He said, "Look, as soon as you shoot a photon out the windowsill, it's going to move the partition slightly, whatever amount." Just enough that you do not know the exact position of the particles. Okay, that was his argument. Okay, so where did these two gentlemen go wrong? Well, they went wrong because they were using this windowsill there, okay? And we're going to replace that windowsill now with a needle, okay? And so now we have a different situation. It turns out that you can do the slit experiment without using the double slits. You can do it just by putting a needle in front. And in that case, if you put a needle, now they have the photons have nothing to bounce against. There is no windowsill against which to bounce. And so the photons should continue straight and never make, that pattern. The explanation is wrong, in other words. Okay? So if we can do it with a needle, okay, it destroys the double slit version of the slit experiment. We should call it the needle experiment, which, by the way, is much easier to do. Okay, and here, let me show you. Okay, I always here's a needle. Okay, I stuck it to a little cork or whatever. I've got a couple of these, so take them with me. So we have, so you can see it better. And I just stick a needle in a cork. You can do this at home, always in the presence of a trained relativist, okay? So here you have the needle, okay? Let's see if we can, and you shine a laser, okay? There's the laser. I'm not gonna shine the laser because it's very hard to hit it, but you shine a light. Imagine that's the laser, and when you look at the wall, you're gonna see the fringes. You're gonna see the fringes with the needle and the laser. Very simple experiment. You don't have to break your head trying to make a slit or measuring the distance and any of that. We don't need any of that. Just put a needle, put a laser pointer, shooting against it at the right distance, okay, and you'll see the fringes on the wall. No problem. I've done the experiment myself, and just don't take my word for it. Just do it. And so the question is, right now, you don't have anything. The photons, the alleged photons, have nothing to hit against to bounce back inwards. And so now we have a problem because now we can't use discrete photons. And even if you use waves, transverse waves, why would they curve around the corner? I mean, we're not talking about water waves. See, they always simulate it with water waves. The question is, light is not alleged to be water waves. They're alleged to be transverse waves, okay? And transverse waves, they just go up and down and sideways, and they go in a direction perpendicular to those two directions, okay, the cross. And so why would they turn a corner? I mean, with water waves, yeah, you can simulate it, but are we saying that light is a water wave, like a water wave? Because if it's a transverse wave, there is no reason for light to turn a corner, which it does. Okay? And yeah, so this is where we have a problem. Under the rope model, it's a no-brainer. The slit experiments. So I'd like to show that, in comparison. Here you have the lights turned off, and you have, I only showed two atoms there being connected. Okay, here I show two atoms again, but many of the connections to every atom on the wall or on the screen. And what you have is when you have the light turned off, okay, there is already a connection between all the atoms. Okay, there is already a connection, but it's not turned on because the wavelength is long and the frequency is high, is low. Okay, what happens when you turn the light on? What you're really doing is you're increasing the frequency, meaning you're making the goosebumps smaller. The wavelength is now shorter. The frequency, in other words, the number of links is higher. And so now you bring it into the visible range. And what happens is the atoms on the side of the needle are relaying that signal from the flashlight to the atoms on the wall, okay, or on the screen. Okay, that's what's happening. That's under the rope model. Okay, so we now have an explanation, a physical interpretation that does not involve magic and all this other stuff that the mathematicians have invented. Okay, and here you see what's happening actually with this with the ropes. Okay, if they're in phase, okay, then and there you see it on the bottom. You see like blue on top and red on the bottom on both ropes that converge upon a given point on the atom. Well, then you have constructive interference and you have a bright light because it's pumping. It's compelling the atom on the wall and stimulating. It's pumping at a faster speed. Okay, and possibly even to a wider range. Okay, maybe there's two phenomena going on in there. On the right-hand side, you see destructive interference, and that's that they're offset. You have the blue on top and the red on the bottom, the threads, right? And the other one has red on the top and blue on the bottom. And so they interfere, they meet at the same atom at the same place, right? We're talking about gazillions of atoms here. I'm just looking at one here, okay? They meet at the same place, and the signal they're receiving are counter to each other. And so the atom does not get that stimulus, okay? So it's not pumping faster, and because it's not pumping faster, the wavelength is below the visible range. Okay, so one has high frequency, short wavelength. The other one has long wavelength and low frequency, and that's how you can tell the difference between a bright spot and a dark spot. The fringes that you see there. So we have an explanation for it, and the explanation really has been around for a long time. It's based on waves, okay, and you heard it. Those who did high school physics know that they explained this with waves. What we've done is simply remove the wave and do it with ropes because there is no physical object called a wave. Wave is a concept. In fact, if you look at all these waves that they show there, both in dynamic and static, you'll see that they're just a bunch of vectors. Vectors which are at 90 degrees to each other to different heights. So anytime you look at a transverse wave, look very closely at what you're staring at. What you're staring at is a bunch of vectors. It's only mathematics. That's what a wave is. There is no physical object called a wave. Okay? In the ocean, it's water. That's what's waving. There's not a wave that's waving. It's a water that's waving. Okay? Flag, it's not known as a wave, it's known as a flag. The flag is waving. It's not a wave that's waving, and so on down the line. And the same thing with light. It's not a wave that's waving because there is no physical object called a wave, just a bunch of vectors, mathematical vectors. That's what they have, values. And they put little arrows there and they confuse you because you think you're looking at an object. You're not. Okay? So keep that in mind. Always when you look at one of those, be aware of what you're actually staring at. Okay, fill on the other side. Give me a second here. Okay, so what have they done? Well, in order to try to explain the slit experiment, quantum really went out of its way because they couldn't explain, so they kept going into the lab and trying to do different things with with the slit experiment. And they put mirrors and they put all kinds of detectors. They put eyes, then they removed the eye. They said don't observe, and then they put the observer, and they went through all this rigmarole just to figure out how Mother Nature's doing this magic trick. And of course today they still don't have an explanation for this. They don't have an explanation that you can rationalize. Okay, and you can see all the stuff that they've done just to try to see what's going on with a slit experiment. And it's like Mr. Feynman said, Richard Feynman. He said, really the slit experiment contains the only mystery of quantum mechanics. If they could answer how light does that magic trick, well, they would know a lot about light, but they don't. They keep doing it with particles. They keep doing it with transverse waves, which are not physical objects. And every time you simulate it with either one of those, first they have a one-way flow. Okay? One-way flow of particles, one-way flow of waves, whatever those are, right? And then they cannot explain it with that either. And they keep putting all these obstacles to try to see if they can detect it. And they finally reach the conclusion that every time you put an obstacle and detect it, you're influencing the experiment. The observer is compelling light to behave in a given way, and then you cannot observe what you're trying to observe because you moved it. That's the issue. Okay, and so let's continue here. This is Einstein. He came up in 1935 and he wrote with Podolsky and Rosen, can quantum mechanical description of physical reality be considered complete? He was challenging Niels Bohr and his Copenhagen Interpretation, saying, look, there are hidden variables that we're not aware of, and that doesn't mean that, that we can never measure, okay? We can never measure. We should be able to measure. All we need to do is find out what all those hidden variables are, all those ghosts that we're not particularly aware of, okay? And a few months later, in 1936, Niels Bohr answered him and criticizing this EPR, this Einstein-Podolsky-Rosen argument, but they didn't have the technology at the time to so-called prove in the lab one way or the other who was right. And were they trying to prove an explanation? No, they don't have an explanation. They don't have any explanations in quantum mechanics. Not one. Okay, they don't have explanations. They have descriptions. Okay, and so what they were arguing about were descriptions. They're saying, look, the description of quantum mechanics is that it's a wave until it becomes a particle, and it becomes a particle when you measure it. At that point, the wave function collapses to a point, and that's why you measure a point. Before that, before you take your detector or whatever, your probe, light behaves as a wave, as I guess a field they would call it. Many waves, we don't know what's going on there. The cat is both dead and alive, and it only collapses to a point, to something detectable, to something classical, you could say, okay, when you measure. At that point, it collapses. Einstein didn't like that. He says, you're saying that we have this fuzzy world out there before we measure that we cannot know anything about. And that's why it became a probabilistic theory. There was a probability of where the photon or the electron could be at. Okay, but they didn't know exactly until they measured. And when they measured, they said, well, it's too late because now the observer interfered with the experiment. And you could say it entangled the experiment. In other words, at that point, there is an interference with a particle you want to measure, whether be it a photon or an electron. Now it's interacting, because there's always distance between particles, right? Now it's interacting with whatever first atom is close by. It's interacting. When it interacts, means it's entangled with it. It now deals with its environment, with a group of particles, not only with a particle that you want to measure. That's how entanglement started getting into this. Well, Einstein and his successors, people like who was it? Bohm, Bohm, yeah. Uh, he, um, he came around the same time, a little later than Einstein, obviously, but Bohm came up with this hidden variables notion as well. He said, look, there are hidden variables, and all we need to do is design an experiment and la la la, but we should be able to figure out how all this is put together. And it was a fellow named John Bell, and he came, a mathematician, obviously. You know, what else can you find in mathematics? Okay, and he came up with an idea. Okay, and really before that we had first the experiment, and the experiment that they came up with an idea how they could test this is with the what is known today as the Alice and Bob uh, experiments. What they do is thought experiments. They have Alice in one place and she measures something clockwise, and Bob is on the other side and he measures something counterclockwise. And when they wanted to see if there was any possibility that you could detect by just measuring by Alice measuring something, they could tell what Bob would see there without measuring. Okay, and some people explain it like, you know, if you had a heads or tails. Okay, well, you can either have heads or tails. Okay, and you can't have both. You do have both, but only one side can show up at a time. Or you can have, like one fellow says out there, two gloves. You know, have left-handed glove and a right-handed glove. And you put the two gloves in different boxes. One glove here and the other one over there. Well, you know, if you open your box and you got a left-hand glove, well, you know the other one is a right-hand glove. Okay? And now, again, that's a description. It doesn't tell me why the other glove is right-handed. Okay? You cannot explain why the other glove is right-handed. Okay, and this is the problem. So the analogy is not quite right. In fact, not right at all. It's a bad analogy. Much better analogy is the rope. Okay, because you know one side can go counterclockwise, and the other side had better go clockwise to the viewer from the other side. I'll show that in a second. But anyways, this is what they show. Where here we have Alice on one side of the world and we have Bob on the other. And they're saying if Alice spins clockwise, well, Bob must, of necessity, spin counterclockwise. And vice versa. If Alice now, you know, you turn her around and she goes counterclockwise, well, then Bob will go clockwise. Okay, so this was the experiment that they designed out there, okay? Or it was a thought experiment, okay? And they designed this and they said, well, unfortunately, we don't have a way of testing it at the quantum level, at the photon, at the electron level. So it's like a moot issue. Yeah, it's a thought experiment, and that doesn't go beyond that. Turns out one fellow, this fellow John, what's his name? Sorry. His name is John Bell. He came up there and he came up with an equation. Okay? He came up with a number. He came up with a calculation. And he says, imagine a pair production, photons. One atom shoots two photons in opposite directions. Okay? He says, well, he came up with this notion of Bell's inequality as it's known today. He says, he looked at all the possibilities and he says, well, there's only 33% possibility that both photons will be detected or go through the polarizers that at either end. Okay, so you put two polarizers like you see at the bottom there. See, have two sensors. Okay, whatever that polarizer means to you, you put two sensors. Okay, and here you detect it. You could say clockwise, spin clockwise. Here you detect it, spin counterclockwise, and they know that's the case always. Okay, because they've done the experiment many times in different ways, ever more precisely. And so Bell just thought, he says, look, there's only so many possibilities. And he came up with a number. He says, look, it's got to be 33% or more of the times that we should have the polarizer detecting the photons going through it. Okay, if you put some interference in there, like a polarizer, something like calcium carbonate, a slab of this material that allows light to go in certain directions, that polarizes light. Okay, but anyways, if light goes through in both cases, okay, there's only 33% possibilities of that happening if you do the calculations right. Turns out when they did the actual experiment, it was greater than 25%. So there was an inequality there because, they said, hold it. This is what our calculations show, but this is what we see in the lab. It's greater than 25% probability. And that's essentially how they eliminated, this hidden variables, at least in the minds of most mathematicians. I'm sure that, as always, there's someone still out there saying that it hasn't been proven to them or whatever. Okay, again, proof is a question of personal taste, how you grew up, how you think. Proof is in the eye of the beholder. We should never use proof in science. Okay, so what happened? Well, one fellow did the experiment quite accurately. His name was Elon Musk, a French guy. And he went out there and he really measured this very precisely. And again, confirmed first that EPR does happen. Okay, confirmed that. I guess his experiment is known the most because it was done very precisely. And second, he agreed with Bell that it eliminated all these hidden variables. There are no hidden variables according to the standard version of quantum mechanics. They continue to insist primarily in the Copenhagen Interpretation, meaning that there's this complementarity. Light is both a particle and a wave. It travels as a wave, and it begins and ends its journey as a particle. That's the official version today. Okay, and again, Elon Musk's experiment essentially did away with hidden variables. Okay, so what's the status today of this thing? Well, this is Brian Greene, and he'll tell it to you in his own words. He says, spooky action at a distance does indeed happen, meaning they cannot explain it. They have no explanation of how two discrete particles, I like to show it this way. Let me get rid of Brian here for a second. Sorry, Brian, I'm going to get you out of here. Bye. You have two particles, okay? And they're not connected, okay? So how does this particle affect this one? If this one is turning, right, it's turning clockwise, why does this one turn counterclockwise? How does this one affect that one? And if you turn this one counterclockwise, how does this one now turn clockwise? If there's nothing in between that, well, yeah, then it's called spooky action at a distance. In fact, you have one fellow, his name is Nick Lucid. He has his show on YouTube. And what this fellow says is that quantum is not magic. Well, it is magic if you cannot explain it, dear Lucid. Okay? Curly, I call him, because he looks like Curly and talks like Curly. But anyways, the Three Stooges, right? If you cannot explain it, it is known as magic. I mean, you get a pygmy. He can get some iron filings and get a magnet and play around with it all day. So he can do it. And he can say, it does, that piece of metal does pick up the iron filings. It does happen. Yeah, and now tell me how it does it. Why does it do it? What's the mechanism? And that's where these people go wrong, see, because they can tell you EPR does happen, entanglement does happen, one particle does influence the other one. Okay, that's so far it's magic, because so far you haven't explained how it does it. And you can't explain it with discrete particles because you got to put ghosts in there. And that's essentially where we have today. We have, all these people with hidden variables and so on. Here you have, all these ghosts and goblins and witches that, move through the experiment, and that's what's happening. They don't have an explanation how, a particle can shoot two photons in opposite directions and one photon influences the other. And the only way you can explain is, like I said before, with a rope. Okay, then in other words, an elongated object. You can use a chain if you want, but you need some kind of elongated object. In other words, this is what I'm saying here, a rope. Okay, so from your end, again, from my end, it's going counterclockwise. Hopefully, from your end, that end there is moving clockwise in your eyes. And if I move this one in the opposite direction, mine is now moving clockwise, and yours had better be moving counterclockwise. Okay, so you can see how easy it was all these years. And yeah, you need an extended entity, assuming my fists are atoms. Then you can explain how one atom influences the other, clockwise or counterclockwise. Without the rope, you have only the two atoms there. How does one atom influence the other if they're all discrete entities? They're not contoured by anything or connected in any way. How do you do entanglement without an elongated entity between them? That's what you got to explain. Otherwise, you don't have an explanation. You're putting ghosts in that same region, and goblins and angels. Okay, so here are my conclusions. Okay, let's get down to the conclusions. Okay, what are conclusions? Entanglement arose when the quantum mathematicians could not explain the Slit Experiment. That's where it all started. 1927, maybe for 8 years, even beyond that, really. They discussed the Slit Experiment. Like Feynman said, it's really the only mystery, okay, of quantum mechanics. If you can explain it, you've got it all solved. And right now, no one has explained the Slit Experiment in a rational manner in the last 100 years. With quantum, without quantum, with general relativity, with string theory, put it all there, they have not been able to explain it. Okay, and so some mathematicians proposed that there were hidden variables. Okay, and Bohm was primarily the guy who fought most for that notion. And Bell's inequality essentially convinced the congregation, the mathematical congregation. Okay, they proved, as they call it in mathematics, they proved that couldn't be the case. Okay, that there were no hidden variables. Okay, so aspects EPR experiment. Okay, first convince them that in fact EPR does happen, entanglement does happen, and second, confirmed in the minds of most mathematicians that there are no hidden variables. Okay. Entanglement starts out where it began. It continues to mean ignorance. Okay, so we should call it quantum ignorance. And my corollary is no experiment, meaning see, touch. Okay, experiment, you're going to go to a lab, you're going to see or touch something, right? No experiment and no equation will ever identify the invisible, intangible mediators that Mother Nature uses to do light, gravity, magnetism, electricity, atomic behavior, etc. Okay, so that's the end of the story for entanglement. Entanglement, according to quantum mechanics, is magic because unless you have an explanation, you are talking magic. And Mr. Nick Lucid, who boasts that quantum is not magic, well, he uses a wave. And there is no physical object called a wave. So as soon as he introduces the wave, we take the microphone away from him. Okay, he can't talk any further until he explains what a wave is. And then, of course, he's got to explain also the atom, why the electron doesn't spontaneously fly away from the atom, what holds it there. In other words, again, we have this entanglement, and the entanglement in this case is between the electron and the proton. They're entangled. Okay, great. That's a description. You're just saying that it is entangled. It stays there. It goes around an orbit within a certain plus or minus region, no problem. That's a description. Tell me why. What causes the electron, first, not to fly away, and second, not to fall towards a proton? That's what you got to explain. If you can't explain that, you don't have an atom. And the same goes for light. If you cannot explain why this photon over there is entangled with this one over here, if you cannot explain that physically, if you cannot give me a physical interpretation, you cannot give me a cause, a mechanism, you don't have a theory, you're not even a scientist. Scientist, someone who can explain rationally. Okay, let's move on to some of the questions, comments people made this week. Okay, here's one. Fellow says, can you demonstrate, more clearly how the diagram of whatever, okay, 15.03 depicts the mechanism of destructive interference? Okay, I thought it was clear. Sometimes I wonder about these fellows because, I mean, if the guy went to high school, maybe even college, I don't know, he should have seen that all this is explained with waves. They talk about interference with waves, with transverse waves. So they show that if the two waves are in phase, it is constructive interference. And if the two waves are out of phase, that's destructive interference. Okay? So all we do is replace the nonsense called wave. There is no entity called wave. You got to find out what is waving, and we're saying it's a rope. And so with a rope, it's the same thing. So I'm not inventing anything new. I'm just saying that the wave is replaced by a rope. All these years they've been confusing what they call a wave, and it was really a rope all these years. And so here's the wave version. Okay, you can see constructive interference there on the left-hand side, and you have destructive interference on the right-hand side. And you see the bright bands and the dark bands. What part did you not understand? Okay, and now we're going to do it with a rope, and the same thing. Okay, and here we see, light coming out of the laser. Okay, it goes through the slits. We don't need the slit. We can put a needle, but in this case we put the slits because it really doesn't matter. And the ropes on the top are connected, and I want you to look very closely at at the last two links close to the right hand side, that atom there that's on the screen. Okay, and what you see is that they're both in phase. And in the bottom one, they're both out of phase. Why? Because there's a different angle in the two beams coming from the slits. You see the angle is different in the bottom one and the top one. I should have labeled those. But the point here is that in one case you got a blue against red, and the other one you have blue against blue, or red against red. Okay, so that's all it is. Nothing fancy. It's just what we've known already for many years. And here again, I show what it is. You have your blue with blue. It's constructive interference. And in that case, you have a bright band, and then you have blue against red, or you have, it's better to say it, blue on the top and red on the bottom, red on the top and blue on the bottom. And now they're out of phase. And so now it's destructive interference. So that's all we're saying here, really, I mean, I'm not sure what part you don't understand. Okay. Okay, let me get rid of this here. Okay, another fellow says, I think it's the same fellow, he says polarization. Okay, says, I hope you haven't forgotten the explanation of light polarization. Okay, let's find out. What is this polarization? Okay, and here I showed it the other day, and what you have is I'm going to look at the top one first. Top one, you have a beam coming in at a polarizer. It could be, again, typical material is calcium carbonate. It's a slab. Okay, you put it in front. Okay, and it's the issue with calcium carbonate is that the molecules are oriented. Okay, the rows of molecules are oriented, and so they could be oriented, for example, vertically. Okay, if you turn the slab around, now they're all going horizontally. So if you put two slabs, one right behind the other, and they're both vertical, like you see there, the green one and the purple one there, right? If you shine a light, well, what happens under the rope model, okay, is that the atom, one atom that I show there, just one atom, we're talking about gazillions of atoms in real life, but here I'm looking at only one atom that's connected to one atom in the flashlight on your laser pointer or whatever. One atom in the slab, the first one, and one atom in the second one, but they're all aligned. In other words, they're all vertical. Okay, so what happens when you turn on the laser pointer? Uh, One atom, again, we're going to deal with one atom. It's complicated enough with one atom, okay? One rope is connected to the other atom, and it's at a certain frequency. In other words, certain wavelength. Now it's visible light. It's at a frequency that within the visible range, okay? And that atom relays that same signal to the atom behind it, which is also aligned in the same way, vertically, okay? And that one relays it to the one on the screen, which is also, well, that one doesn't really matter, just stimulates the atom on the screen, period. And it's lit, as you can see, it's lit. Okay? The one on the bottom, what happened? Well, now we turned 90 degrees the second slab. Could be the first one, it doesn't matter. You turn the second slab of calcium carbonate and you turn it at 90 degrees to the first one. So now the molecules of that second slab, the green one, are horizontal. The first one is vertical, the second one is horizontal. What happened? What happened just to two atoms, the same two atoms that we had before? Well, now you can see the location of that atom is different. And I drew the rope there, even though the rope, remember, goes behind the first slab. But I drew it just so you can see the direction of the rope, how it goes down and then up. Okay, so something's happened to that specific atom, that pair of specific atoms that were connected first in a single direct line directly to the screen or to the wall. And now you turned it around and now they're not on the same axis. Okay, and I showed that the other day. Let me get rid of this. Oh, let me get this one too. We're going to be dealing polarization here, so you know. This is my little gadget just to show the mechanism, okay? Put it in reverse here. Okay, so here you have the ropes, okay? Here, that's what I'm showing, okay? So here you have the ropes, okay? You can see what I've done here. We have two slabs, okay? Really three, I got two of them together. You have two slabs, okay? And you have the ropes that interconnect four atoms, okay? What happens when you turn one of them around? Well, you can see that the atoms are no longer on the same axis. They were here on the same axis, very straight, directly. You know, light is coming from my left or from my right. When I turn one of them around, they're no longer, those specific atoms are no longer on the same axis. So the beam is extinguished. You do not get relaying of the signal along the rope to the one on the wall. Okay, so that's the mechanism. Okay, but there's another mechanism going on. It's got to do with the slit experiment, and that's that, you know, when you turn it around, all the ropes that are connected only within the system, let alone the ropes that crisscross the universe or that come from the sun and all that stuff. We're talking only about the ropes that interconnect the slabs and the laser pointer and the screen. That's it. Let's just look at those ropes. Okay? When you turn one of the slabs around, you're also torquing the rope at a different angle. You already gave it a quarter turn. All the ropes. So not only don't you have relaying in a straight ahead forward manner because you turn one of these slabs at 90 degrees horizontally, you also have twisted the ropes, every one of the ropes. Like, you know, if you have it like this, right? It's not the same thing as to have it like this, you know. You're twisting it like that. You're twisting the rope also a quarter, 90 degrees. So you have all these effects. So just to understand the linear polarization, let alone circular polarized light, but just straightforward linear polarization is a monster. Okay, so all I can urge you is to look at that first. Okay, and let me show you a little more. Let's go a little deeper here because I want to show you something else here. Okay, this is from my book. Okay, the rope hypothesis, downloadable. It's free. Okay, and this is around, I think, page 135 or thereabouts. So it's towards the end of the book. And there you see the three situations. Okay, The first one on the top, okay, shows that you have the ropes in a north-south direction, and they're all in a north-south direction because the slabs are vertical, okay? In the middle, center group there, now we're going to rotate the second slab into the east-west direction. Well, what happens? Because you rotated 90 degrees, right? So now the row of molecules that make up the slab, they're no longer vertical, they're horizontal. And I'll call it east-west. So what happens? Look at what happens at the rope as soon as it touches each one of those atoms. Well, in one case, it was blue on top and red on the bottom, and the other one is the other way around. Okay? And so what are they going to send to the screen? Well, remember, we're talking about gazillions of atoms here, but some of them are going to be red on the top and blue on the bottom. The other ones are going to be blue on the top and red on the bottom. And so you're not going to get any light, not only because you've twisted the rope, but also because the atoms are now no longer in the same direction, and they're not relaying the signal to the wall in the same on the same axis. What happens when you put a 45-degree slab between those? Well, you start reestablishing the beam because now you gave the ropes a quarter turn. Okay? So all these effects have to be analyzed in detail, and it's a monster just to look at this alone, let alone, if it's circularly polarized light. Just to look at linear, that's a monster on it. That's a whole course. Okay, but let's go a little deeper, just so you see why that's the case. Okay, we're going to go into a deeper why here, cause, a mechanism. Okay, and here it is. And that's also in the book, so it's for free. Look around, I think it's page 135, 131, something like that. You have calcium carbonate, okay, and you have these little men. Well, they're not little men, okay? That's what the molecule looks like, okay? Calcium carbonate 3, CaCO3, okay, looks like that. That's more or less the aspect of that molecule if you were Atom Man and went down there and looked at it. So it looks like a little a gingerbread man, okay? That's what they look like. So the first one, front view, completely towards the left, okay? You're looking at it straight ahead. You're looking at, there's your eye, okay? You're looking at straight ahead. And we're only going to look at a couple ropes here. We're not going to look at the gazillions of ropes crisscrossing just two of these molecules. Okay, there's a lot of ropes crisscrossing there alone. Okay, but we're just going to look at the main ones that we're interested in just to show you the mechanism. Right now you're looking straight ahead, and you're looking at one in front, the other one behind. These are the molecules that belong to each one of the slabs. You got the first slab and the second slab behind it. Okay. Now you're going to rotate, that's the second set there, okay, slightly to the right of that. You're going to rotate one of these slabs. What you're doing is rotating the molecule. And now you can see what's happening to the ropes. They don't get tangled, remember. It's just that they're not on the same axis anymore. That's why you extinguish the beam, okay? And then on the right-hand side, of the black line, dividing line there, you see again, but this time you're seeing it from the side. You're looking at the same molecules, but now you're looking at them from the side. You're looking at side by side. You have the first slab there and the second slab, okay, and these are the molecules that comprise these slabs. And you can see what you're doing when you're rotating the second slab, okay? The atoms are no longer aligned. They're not on the same axis, okay? So this is what's happening in there, okay, when you extinguish the beam, why a polarizer works, okay? That's the mechanism we are proposing, and yeah, it's a monster just to understand this alone, because you got to look at what's happening to the ropes. And remember, calcium carbonate has calcium, which has many atoms, essentially many hydrogen atoms comprising calcium. You have many, 8 comprising carbon, okay, 8 ropes, because you got to think of every hydrogen atom that comprises carbon, which is 8 of them. Each one has a rope, okay, And so when you look at this, you're looking at many ropes just for one molecule, let alone from the fact that, a slab of this stuff has gazillions of molecules, let alone atoms. And all these ropes are there. So you've got a three-dimensional spider's web, very, very dense spider web. And you're going to rotate this thing. So, you got to try to visualize this, and it's not easy. Not easy at all. The best thing is to try with one atom at a time, which is what I did here, and try to visualize that and understand the mechanism. Then, if you want to beat your brains out, go ahead and put more ropes in there and twist it around and see what happens. Okay? But I think the important part is to understand the theory, and the theory is the mechanism, an explanation of the mechanism. Okay, one fellow says, info theory. Okay, he says, please make a lecture about information theory. He went to a site, and I guess they gave him a lot of slack about information theory, and saying that, I guess some religious folks, they say that DNA is information from God, that God made that message and sent it to us, and so on. And so he didn't have really good arguments to counteract that. And so he said, he went there and he says, information can only be produced by an intelligent being. I don't know. I don't think that was his statement. I think that's one of the statements he got from this site. That's what they hit him with. And then God created the information in the DNA. Okay, so this is what they hit him with. So he says, do a lecture on this so that he can have some arguments, or, to counteract these people. Okay, I dealt with information in the past, a couple months ago at least, but let me show you right up front. This is from my other book, Why God Doesn't Exist, okay? And I'm not going to read all that. I just want you to focus on one part there that came out of that book. It says, DNA contains no information in itself because information is what an extrinsic observer derives, okay? DNA is not a message. DNA is not information. People, the mathematicians have confused all this stuff completely. They talk about sending information, receiving information. They treat information like a physical object. Information is what you get out of anything. Okay? There is no, DNA is not information. DNA is a molecule. It's just a bunch of atoms put together. That's all DNA is. Now, you look at DNA and you say, oh, I understand this, or I understand that, or I can describe that. That's information. Information what someone gets out of it. You don't send information. You receive information, so to speak. Information is only on the receiving end, and the mathematicians never learn that. So they talk about sending information and, and how fast information travels, and shows you what kind of idiots they are. They are truly idiots. Idiots meaning people with big ideas, idiots, okay, and we call them idiots. And so DNA or anything, you read a book, the book is not information. Information is what you get out of it. Your understanding, that's information. Okay, so let's get that right. Information is only on the receiving end. You never send information, you always receive information. Okay? So let's get that part straight. But yeah, one of these days, maybe I'll give another lecture on information. I don't have it in my things to do right now. I've got other issues there with quantum mechanics. And so right now I'm doing a series really on quantum mechanics. And no, there is no information in quantum mechanics because they have not learned anything from quantum. They cannot explain anything, so they have no information. Okay, they keep transferring the information, never receiving it. Okay, another fellow says, I have a small problem with the rope theory. Well, it's a rope hypothesis. I don't really have a name for the theory. I call it the thread theory, but even that, thread is a hypothesis. It's an object, it's a thing, but that's how I divided it. Maybe someone smarter than me comes up with a better name for the theory, okay, which is the explanation of the mechanisms. Rope is an object. It's a hypothesis, an assumption. Okay, of gravity after learning about Lagrange points. These Lagrange points are locations where the balance of gravitational pull allows satellites to remain stationary with respect to the Earth-Sun system, without them wandering ahead or behind relative to the Earth's orbit. Okay, what I want to know is how L2 and L3. Okay, he gave me a description of L1 through L5. Okay, and he wants to know L2 and L3 are possible if the ropes that connect the satellite go through both the Earth and the Sun before getting to the satellite. In other words, well, let me just continue reading this. I thought gravity is a function of the number of independent ropes. It is. Would ropes going through the Sun and the Earth make them no longer independent and only pull as much as the nearer one? Okay, more or less yes. Yes, and let's see if we can make sense of this. What he's asking essentially is, you have the Earth and the Sun. Okay, Earth and Sun, and here you have the satellite. And the Earth, remember, Earth goes around. And so the satellite is sometimes between the Earth and the Sun, and sometimes at the other side, and sometimes it's on the sides. Okay, so you could say it's parallel to the Earth with respect to the Sun. So we have all these three situations: in front, behind, and to the side. Okay, those are the three situations. And the first thing we have to just clarify, okay, that there are gazillions of ropes crisscrossing our solar system. We call it the cosmic background radiation. It's all those vibrations, okay, gazillions of ropes that are just sending light, and all this fuzziness out there, which they claim fills all of space. It doesn't. It's just ropes within space. Each rope is very well delineated, okay, specified. But you have gazillions of ropes, and I just put it there in crisscrossing in different directions to show that our solar system is crisscrossed by gazillions of ropes that come from the other side of the universe and go past us. Some die at the Sun, some die at the Earth, others go directly past us. Okay, so we have all these ropes just crisscrossing in our solar system. Okay, that's the first thing. Just keep that in mind. And there we have the three locations for the Sun, for the Earth, and that bright little spot near the Earth, right at the bottom and on the side there. Those are, we'll call that the satellite, that beige, bright beige. And keep in mind, we also have Mercury close to the Sun. We have Venus there. Okay, and those two are also connected to everything there, but they're too far away. Okay. It's very important to know that they're very far away. Okay, distance here. Remember Newton's equation. Distance is of the essence here. Okay. Okay. So this is what they look like. Okay. Here we have the three locations for the Earth. We have the satellite there. Okay. And in one situation, which is the one on the lower left there, we have the the satellite is between the Sun and the Earth. And the second position there, it's to the side of the Earth, and then the other one, it's behind the Earth. Okay, and so we have these ropes coming from the Sun, in one case, going right through the satellite to the Earth. In the other one, you have ropes coming separate, some to the Earth, some to the satellite. And then the other one, ropes go through the Earth and go to the atoms that comprise the satellite. Okay, so those are the three situations. Okay, that's essentially what he wants to know. What is the difference, or how do you handle this? Okay, and here let's look at a simpler version. Here we have what I call the bird's beak. Okay, this is important because it's a function of distance, square of the distance in case of light, but it's a function of distance. It's an inverse function of distance. The farther away you are from an object, the more the ropes come together and form, you could call a single coaxial. They're almost on the same axis. So gravitationally, they're weak. They don't pull. The only way you can get that quick acceleration, in fact, you get acceleration, is when you're within the bird's beak. Okay? And the Sun has a long bird's beak compared to the Earth. The Earth has a small bird's beak. And here I just show the difference in bird's beak. But the important part is that between the ends of the two bird's beak, and the bird's beak just continue extending. But for the most part, okay, we have what I call the linear regime. Most of it is essentially a single coaxial until it comes to our area. And a lot of people have a problem visualizing that because they say, well, hold it, from the edge of the earth to the edge of the sun. Yeah, it doesn't matter. It doesn't matter because those are very few. That's why I didn't draw them. Okay. The important ones are the ones are where the big coaxial is at, and that's through the center. Okay. So you do have ropes connecting edge to edge from the sun to the earth, but in comparison to the ones that come in the main axis, they're almost irrelevant. And again, remember the sun is very far away. In fact, we see the sun about the same size as the moon, which is close by and much smaller. Why do they look the same pretty much in size? Because one is very far away. And again, the moon exerts a little more influence, or just about maybe the same amount of influence as the sun. I'd say the moon is a little more powerful than the sun as far as gravitationally, because it's the distance makes the difference. It's just much closer by. So here is the final version of that. And you see the two little electron. You see the two satellites, okay? And one satellite's in front and the other one's behind, okay? And what's the issue here? The issue here is, first, the Earth exerts a much more powerful influence over the satellite because the bird's beak, let's assume the satellite is just at the edge of the bird's beak of the Earth, okay? It's far enough away where the bird's beak towards the sun, of the ropes connecting us to the sun, that's where the bird's beak ends. And that's where we put the satellite. Same, the one on the other side, okay? And so what happens there is you're talking about the satellite and only the ropes that are connecting the atoms that comprise the satellite to the atoms that comprise the sun. Well, it really doesn't matter that much because remember, the Earth's bird's beak dies right there, very far away. And then what you have is essentially a single coaxial of the atoms of the sun that are connected to the atoms that comprise the satellite, okay? So yeah, even the satellite have a tiny bird's beak there, okay, for that matter. But the point here is that, most of that, the sun exerts almost no influence gravitationally over over the satellite, over anything, okay? The only thing the sun does really is prevent the Earth from flying away. Is it because it's pulling on it gravitationally? You could say it is any more or less like this. Does my finger, which in this case would be the sun, pull on the ball gravitationally? It doesn't have to. It just has to be equal. In other words, the rotation of the Earth around the sun has to equal the strength of pull, you could say, of this rope that connects us, of all the ropes that connect us. But if the Earth just goes back and forth slightly because the Earth also goes, the sun goes also around the Milky Way, so it swings it Keplerian-like. Sometimes the Earth is a little farther away, sometimes it's closer by. It's not a perfect circle. But if you swing this thing around, okay, you're not talking about gravity per se. What you're talking about is that the sun is just preventing the Earth from flying away. It is, in other words, the Earth, if the Earth were not orbiting the sun, it would drift towards the sun eventually. It would fall into the sun. But as long as it's going around, it just maintains essentially a static position with a slight variation only because the sun itself is going around the Milky Way and swinging the Earth around itself while it does so. Other than that, what you have is this long coaxial, and it just prevents the Earth from flying away. That's all it does. There is no real gravitational pull, okay? If the Earth were not going around the sun, rotating, it would gradually fall towards the sun, only because now you don't have this centrifugal force, okay? Other than that, the only purpose of the coaxial is just to keep the Earth in place. And it does the same thing to the little satellite. It doesn't affect the satellite gravitationally in any significant way, any more than the moon does. Now, all these objects, the Earth, well, the Earth to begin with, really, but Jupiter, Venus, all these planets exert some influence, very tiny influence over that satellite, and the satellite does not um, always keep its exact distance from the Earth. The satellite does move a little bit as well because of all these influences. Maybe they're not measurable, maybe it's very slight, but the satellite does not maintain always the same exact distance. Okay, and again, it's because all these celestial objects influence it, but very little. You know, the gravity that you can get from Jupiter, even from the Moon, which is closer by, is is um, is very tiny. In fact, the moon does affect, for example, the tides, according to Newton, and that's very possible. Okay, but again, you know, it's not like it affects you. You know, it doesn't affect the tides to the point where it pulls the water off the earth. Okay, so yeah, the moon affects the tides, but its influence is very light. And the same thing with a satellite. All the celestial objects in the solar system affect our satellite, but it's as much as they affect you, which is like astrology, which people say that the stars influence us so much, especially when we're born, that it gives us certain tendencies and so on. Well, go study astrology and, and then you'll figure out if it's true or not. Okay, folks, I'll see you on Wednesday, and I'm going to have Ans with me, and we're going to do some question and answers real time. So get your questions ready and throw all the rotten tomatoes you can at our faces. We'll see you then. I'll see you on Wednesday. Bye bye.